Okay, so okay, so we're gonna do the starter question really quickly. In fact, if you got the practice done for last night, and I'm gonna have you hand that in before you leave. This should be very easy. The first thing you'd want to take note of is, remember, because these have different coefficients and they're the same signs, it's going to be an ellipse. We know that for a fact. You want to make sure that you're grabbing things in order, that you pay attention to what numbers are associated with what variables. So you'll notice that this does have the x first, so it's pretty easy to find the h and the k. So this has a center, and I'll actually write out the word center. The center is going to be 1, negative 1. So if we were to graph this, 1, negative 1, and then we're going to go 3 units in the x direction, 1, 2, 3, right there, 1, 2, 3, so right there. And then we'll go 5 units up here and down here, and then we'd label all of those, right? Now, when we did this yesterday, I said to kind of make it look right, I said you can put a little box around here, and I said, I don't do that all the time, but sometimes it makes it easier to, as you're kind of going around there, especially when I draw these on this tablet here. Sometimes it's hard to make it look really nice. And if you have a box, it kind of guides how close you're going to get to the edges and stuff like that. It kind of makes it a little easier to make it symmetric, okay? So that's how you graph an ellipse, and hopefully going through and practicing, you got enough of a sense of how those work. Now we're going to talk about hyperbolas. Hyperbolas is by far the most complicated conic section. Yeah.
On an ellipse, the endpoints of the major axis are the vertices.
Those are the vertices.
So what are the endpoints of the minor axis?
Some people call them vertices. It depends on your textbook and your teacher. They don't really have a name to my knowledge. You could call them minor vertices or something like that. In fact, that would maybe be a good way to distinguish, but to my knowledge, they don't really have a name. Good question. Okay, everybody good there? Okay, so let's talk about the definition of a hyperbola, because just like the other conic sections that come from different definitions, we've got a definition for a hyperbola. A hyperbola is the set of points on a plane, the difference of whose distances from two fixed points is constant. So those two fixed points, again, are still going to be called foci. And you'll remember that yesterday when we were talking about ellipses, it was the sum of the distances was always the same. On this one, it's the difference between those distances. Those are always the same. Okay? So I'm going to pull up a little animation here. Okay? And those points where those lines intersect. So the hyperbola is this piece right here. This yellow distance right here is the distance from the point on the hyperbola to this focus. This green line right here, blue line right here, is the distance from that point to the other focus. Okay? And then the difference between this yellow line and this blue line, that difference always has to be exactly the same. Okay? So I'll keep playing that. We'll stop that again. Okay, now if I take this point right here and say I figure out what this distance is right here and figure out what this distance is right here, okay, and I calculate that difference. Let's say that difference is 10. There are actually two places on this plane over on this side where I can find a point that has exactly the same distance from this point as it does, the difference between those distances is exactly the same. So if you look at this animation right here, you'll notice that this focus right here has a circle around it. Okay? So there's the circle around that focus. There's the circle around this focus right here. Okay? And so what we're doing here is we're figuring out, this is kind of like the radius of this circle. Okay? This one right here is the distance to that point on this circle over here. Okay, and those circles are just getting bigger and bigger and bigger. So you can kind of see where this distance comes in, and it's in comparison with that distance right here. So we get this branch, this hyperbola over here, and you'll remember I did one of these on the board with the flashlight earlier this week. So that right there is this branch of the parabola. But then because we have two foci, we can have this shorter distance be to this focus and this longer distance to be to this other focus right here. So we actually get two branches. So this green thing right here, in fact, let me turn this off so we can see a little bit better. This curve right here, that is one branch of the hyperbola. And then this green curve right here, that's the other branch of the hyperbola. And if we just let this continue, I think the circles and everything disappear at the end. Down here you can see the comparison between the yellow and the blue. And they're kind of cool shapes. They're pretty darn complicated. But again, when we graph these, we're going to be interested in, this is the actual graph that we would do, okay? We're not interested in drawing any of these other lines or anything like that. Now we'll label some other points like the center, and there we go. That's what it looks like, okay? We'll label the center and stuff like that, and the foci and vertices and all those sorts of things. But the actual hyperbola is just that, those two curved parts, okay? All right, so from previous sections, we know that hyperbolas have two squared variables that have different, not quite, just different signs, okay? So all it takes is just different signs. So one of them, when we put them on the same side, one's going to have positive and the other one's going to have a negative, okay? And just like all the other ones, we're going to have perfect squares in that graph-friendly form. Now, you remember we learned a bunch of vocabulary that went along with ellipses, okay? We've got a ton of vocabulary with hyperbolas. So we've got a center, as you'd expect. There are two branches, two foci, two vertices. We've got something called a transverse axis, something called a conjugate axis, a fundamental rectangle, and that's really important. And then we've also got some asymptotes, okay? Now, of all the things on here, the only thing that is actually part of the graph and the curve is just those two branches, okay? Everything else is important information about the hyperbola and helps us graph the hyperbola, okay? But it's not actually part of the hyperbola. Okay, so let's take a look at this first example right here. This is in a nice graph-friendly form. You'll notice that it looks very, very familiar. The only difference between this and an ellipse is what? The minus sign. It's a minus rather than a plus. Because they have different signs, we know this has got to be an ellipse. Or sorry, got to be a hyperbola. Okay, where's the center going to be? Okay, so here's how cool this is. Act like you're graphing an ellipse. So the center is going to be 0, 0. I'm going to go 3 units in the y direction. I'm going to go 3 units up and 3 units down. Then I'm going to go 4 units to the right and 4 units to the left. Okay? That rectangle that I drew yesterday isn't as important on ellipses as it is for hyperbolas. Okay? You really have to draw this if you're going to draw an accurate graph. Okay? This is called the fundamental rectangle. Now, unlike an ellipse doesn't stay inside the box. It doesn't open inside the box. It opens outside the box. So here's what we do next. Okay, we're going to draw the diagonals of that box. So take the fundamental rectangle, and we're going to draw the diagonals. So make them line up as best you can. Make them as straight as possible. And then we've got some decisions to make. So let's catch up in these instructions over here. Okay, so this equation right here is a hyperbola with a center at 0, 0. We already looked at the number underneath the x squared term, and we went that far in each of the x directions from the center of the hyperbola. We looked at the number underneath the y squared. We went that far. And we used those 4 points right here to define the sides of the fundamental rectangle. Okay? Then we drew the diagonals. Okay? Let's talk about what those diagonals are. Okay? Knowing what this vocabulary is up here, what would you guess goes in this blank? Could be some axes. They're not really symmetric, though. Usually an axis. Okay, these are asymptotes. These are going to help us graph the correct shape. They're going to help us make it look right. Okay? This is really important. The next thing is the hyperbola opens in the direction of the positive variable. It opens in the direction of the positive variable. So it doesn't matter which number is bigger. Doesn't matter which one's smaller. It matters only which one is positive. Okay? So lots of different things when you blend all these together. Again, hyperbolas aren't that bad. When you mix them all together with ellipses and parabolas, then it gets hard to remember what's what. So you've got to remember this. On a hyperbola, it opens in the direction of the positive variable. So which variable's positive? Y. So it opens in the y direction. So here's how you draw it. Okay, I don't care which side you start on. I'm going to start over here. Okay, the parabola is going to run along this asymptote. And then when it gets here, it's going to curve in and it's going to hit this point right here. So that point is a vertex for that branch. Then it's going to come back out and it's going to curve up and it's going to get really close to that line. We're going to put an arrow on each one of the ends. Then it does the same thing for that bottom branch. So it's going to run along here. It's going to curve inward. It's going to hit this point right here. There's the other vertex. And then it's going to continue on that curved path. And it's going to go like this. We put arrows on the ends. And there we go. Now, we just graphed the parabola, but we haven't labeled everything. So we want to label all the important parts here. Okay? So again, the center is 0, 0. This vertex would be 0, 3, and this one would be 0, negative 3. And then we've got to find the foci. Okay, now, the foci are C units away from the center along the, okay, here's what we call this. We call this the transverse axis. Okay, think of like a transcontinental flight or something like that. You go across. So the transverse axis slices right through both branches. Okay, so this is called the transverse axis. The conjugate axis is the one that goes right in between them. It doesn't touch either one of them. It doesn't cut across them. It goes right through the middle. So this is the conjugate axis right here. This is the transverse axis. Okay, now if you'll remember the other day I said foci, or the focus for a conic section, is always inside the curved part of the conic section. So we're expecting to find a focus in here and a focus in here, inside both of those curved parts. Now, here's how we tell where it is. Again, it's always C units along the transverse axis. We're going to go C units from the center up and C units from the center down. And notice how nice this formula is. It's just the Pythagorean theorem, right? Okay. We could actually see where it's related to the Pythagorean theorem, but this is a good way to think of it. Okay? With the ellipse, we had to subtract the small one from the big one so that it could be inside the box, so the foci could be inside the box. With a hyperbola, the foci have to be outside the box, so we're going to take a squared and b squared and we're going to add them together. So in this particular case, if we add those together, what do we get? 25, and then we take the square root. So in this case, C is going to be 5. So that means I'm going to go up 1, 2, 3, 4, 5. I'm going to put a focus right there. And 1, 2, 3, 4, 5. I'm going to put a focus right there. So 0, negative 5, 0, positive 5. So there are the foci. Okay? Any questions? Okay, nearly done. We've labeled everything we need to on there except for we need to label the asymptotes. Okay, so here's how the asymptotes work, and I need you to stop and think about this for just a second. Okay, we're going to have y equals, now notice I've got this in point slope form, so I've got y minus k plus or minus a slope and then x minus h. Okay, now on this one, h and k were both 0, right? So this is going to be y equals, then I'm going to have a plus or minus. I need to figure out what the slope is, and then it's just going to be an x. So here's the cool part. Here's how you figure out what the slope is. A lot of people struggle with the asymptotes on a hyperbola. They're actually very easy if you think about them this way, okay? So I need to figure out what the slope is of this line. To figure out what the slope is, I just think rise over run. So I'm going to go up this far and over that far. Well, how far did I go up? 3. And how far did I go over? I went over 4. Aren't those these numbers right here? The rise would be 3 and the run would be 4, so the slope would be 3/4. Everybody good with that? And this one would be down 3 and over 4, so the slope on this one would be -3/4. Well, stop and think about this. If slope is the rise over the run, wouldn't whatever we go up or down from the center, wouldn't that always be determined by the number underneath the y? And wouldn't the right or left always be the number underneath the x? So the quick way to figure this out is think rise over run, but this is always going to be the one associated with the y variable, and that's always going to be the one associated with the x variable, okay? So in this case, it's either take the plus or minus, take the square root of that, I put a 3 on the top, take the square root of the number underneath the x, and there we go. There are the two asymptotes. Okay, are there any questions there? Does that make sense? Yeah. The conjugate axis is the one that runs right between the two branches. Okay? And you'll see why they call it the conjugate axis when we do one that's a little more complicated. Okay, any questions? Okay, this is a ton of information. Look how big that box is. Look at all those points. Okay? I think it's a lot easier to just think of it this way. Okay? Think of graphing a hyperbola just like you'd graph an ellipse, except for the branches open outside the box. Hyperbola is open in the direction of the positive variable. It's the same formula we used before, only we're going to add the a squared and the b squared together to figure out what c is. Because we got to add them together so they'll be outside the box because the branch is open outside. Okay, and you can use the center of the box and the diagonals to find the asymptotes and write them in point slope form. Okay, and this is what I was talking about up here. So let's do this. Okay, I don't think I've done this with a class before, but let's do this. Let's figure out what the asymptotes are first, and then we'll come back at the very end and we'll just confirm that we got it right. Most people struggle with asymptotes. Let's see if we can get the asymptotes right from the very beginning. The cool part about this is, here's all you have to do. See the stuff with the y? See the y minus, or the y plus 1? That's what we want right here. So I'm going to write y plus 1 equals plus or minus. I'm going to figure out what the slope is in just a second, and then I'm going to write x minus 8. So that's going to be x minus 1 in this particular case. Everybody good there? Okay, I need a fraction right here. I need a rise over a run. Which variable has to do with the rise? The y does. So I'm going to look underneath this. I'm going to take the square root, and I'm going to put a 3 right there. Look underneath this. Underneath the x, take the square root. I'm going to put a 4 right there. Those are the asymptotes. We'll confirm that in just a second. Okay, any questions? Okay, let's go through and graph this. Where is the center going to be? Okay, careful. You got to grab this one first, right? So that's going to be 1, -1. So we're going to put that right here. How far do I go in the y direction? 3. It's just like the one up above. And in the x direction, I go 4. Those define the end points or the sides of the box, the fundamental rectangle. So we're going to draw a little box around here. Start way out here. Make sure you go through the center. Okay, there's the asymptote going that way. There's the asymptote going that way. opens up and down, right? Doesn't it? Okay. So I'm going to put a point here and a point here. Please darken that point in. Those are the vertices. And then you know where to aim once you're running along here along these asymptotes. So I'm going to run along here. Curve around and head out there. Put an arrow on each end. Run along here. Not a whole lot of room to make this, but we'll survive. There we go. So I've got a center of 1, -1. I've got a vertex of 1, 2, and another vertex of 1, negative. Let's see, what do we got here? -4. And then I need to know what C is. C is going to be, let's see, I add those together. So that's going to be 16 plus 9. So C is going to be 5 again. So I go up 5 and I go down 5. So that's going to put a focus right here at 1 comma. Let's see, if I went up 5, that's going to put me at 4. And if I went down 5, that's going to put me at -6. Okay? So if I've labeled those 5 points right there, and I've labeled the asymptotes, that black graph right there is what we're after. Okay, are there any questions? Sure? Okay, take a look at this. This is in point slope form, so this should go through the point 1, -1 and have a slope of either plus or minus 3/4. Does it go through 1, -1? And is the slope of this line right here positive 3/4? And is the slope of this one negative 3/4? It is. That's it. End of story. Got the whole thing. Okay, any questions? Quite a bit more complicated. Quite a bit more complicated. Okay, let's take a look at a couple that are a little bit more interesting because the numbers work out in kind of a strange way, and you'll see why they figured out some of these names here. We probably won't do both of these here. I think both of these are pretty easy, but we'll just talk about the difference. Okay, on this problem right here, first of all, what's the center? Center's the origin. How far do I go in the x direction? 3. In the y direction? Only 2. And I'm going to draw the fundamental rectangle. Now, for this same fundamental rectangle, I could have 2 different hyperbolas. I could have one that opens up and down, and one that opens right and left. So when I'm drawing these asymptotes in here, I start thinking about, well, it's either going to be up or down, up and down or right and left. How do you tell which it is again? The positive one. So this one opens right and left. So let's go ahead and put these points right here. There's a vertex here and a vertex here. Okay, now, I haven't dwelled on this very much, but let's talk about this for just a second. What happens here with a hyperbola, and I'll talk about an application for this in just a second. The reason this is an asymptote out here is because, remember, the difference between these 2 points, the difference between the distances between the point on the hyperbola and the 2 foci, that difference has to be constant. Well, the further you get away from it, the harder it is to tell that there's much of a curve to this. It actually turns into something of a straight line. It gets really straight out here, comes here, and then it kind of curves around, hits this point, and heads back out this direction right here. Okay? Same thing on this one, runs along here, hits this point, curves around, hugs along that line right there. Okay? Gets closer and closer to that asymptote. Okay, the vertices are pretty easy to spot. We've got our center here at 0, 0. This one's at 3, 0. This one's at -3, 0. The foci are a bit of a pain on this one because if I add those 2 together, what do I get for C? I get radical 13. Okay? So I'm going to go radical 13 this way, which is a little under 4. So I'm going to put it about right there. So there's a focus. I'm going to say that that is radical 13, 0. And then I'm going to put the other one over here. So that one's negative radical 13, 0. Okay, any questions? Okay, what don't we have? Asymptotes. Okay, so the asymptote's going to be grab the expression with the y equals plus or minus some fraction, and then the expression with the x, it's just a plain old x, so we can just write an x. The rise is associated with the y, so this is going to be a 2, and the run is associated with the x, so that's going to be a 3, and that's everything we'd need there. Okay? Any questions? Sure? Okay, take a look at this one right here. What's the difference between this one in example B and this one in example A? The only difference is, you'll notice that underneath the y is still a 4, so we'd go 2 in each y direction. The center's still 0, 0. We're going to go 3 in each x direction. The fundamental rectangle is going to look exactly the same. The asymptotes are going to be the same. The difference is, because y is positive, it's going to open up and down instead of right and left. Does that work? Okay. Let's see if we can get a couple more in, and then I'm pretty confident you'd be able to do this assignment. If it needs to spill into Tuesday, we'll let it spill into Tuesday, and I'll tell you how much of the assignment I want you to do. Okay. This is in graph-friendly form. Okay. I would recommend, you don't have to do this, but I'm going to write down that the center is at 2, -1. I'm going to write down what the asymptotes are. Okay, the asymptotes are, grab the expression with the y plus 1 equals plus or minus. We're going to make a fraction. Grab the expression with the x. What goes on top? A 3. What goes on the bottom? Radical 7. That's a nasty looking equation for a line, but that's what it is. Ugly looking slope. Okay, so there's the center, there's the asymptote. So let's come over here. 2, -1. So we're right there. In the y direction, we're going to go 3. In the x direction, we're going to go radical 7. Radical 7 is in between 2 and 3, so I've got to go, let's see, over to about here, I'd say, and over to about here. And I'm going to use those points to define the sides of the fundamental rectangle. So if we had to talk about eccentricity on this particular one, are these very different? Probably not much eccentricity. Draw in the asymptotes. Opens left and right. Okay, you got to get used to that. Everybody listen, please. When we put all these together, in particular with hyperbolas and parabolas, the rules are completely different. Okay? If you have an x squared with a parabola, which way does it open? Up and down. Okay? If you have a y squared, it opens right and left. That's a little bit weird. The rules are completely different here. First of all, they have 2 squared variables, so you can't rely on that at all. And it's only determined by which one is positive. It's only determined by which one is positive. So if x is positive, it's going to open in the x direction. If y is positive, it's going to open in the y direction. So this is going to open in the x direction, so I'm going to put a big fat point right here and a big fat point right there because both of those are vertices. It's going to run along those asymptotes, so it's going to be really straight, and the closer it gets, the more curved it gets. Going to go like that. And then same thing over here. These 2 branches should look very symmetric. Make them look like that as much as you can. We'll put the arrows there. Okay. And then let's label these. How do I label this point right here? Okay, what is it, Tammy? 2 plus radical 7 comma -1. And what's this one? 2 minus radical 7 comma negative 1. Okay, and then we want to find the foci. So we add those together and we end up with the fact that C is equal to 4. So I'm going to go 4 units over here and I'm going to go 4 units over here. So there's a focus there and there's a focus there. This one happens to be at, if I do 2 plus 4, that would be 6 comma negative 1. And this would be negative 2 comma negative 1. Oops, make that look right. So I've labeled all 5 of those key parts of the definition or the graph. I've got the asymptotes right here, and I'm all set to go. That's it. Okay, now here's why they call this the conjugate axis. In fact, let me change colors. Try again. Conjugate axis. This one right here is the transverse axis. Okay? So this is called the conjugate axis because notice how things appear on either side. Notice over here the x-coordinate is 2 plus radical 7, and over here it's 2 minus radical 7. And what do those have to do with each other? They're conjugates. Okay? That's where the name comes from. And the word transverse, if you transverse something, you cut across it. So there we go. Okay. Any questions? Okay. Let me just look at this other stuff just so we're aware. Are these in graph-friendly form? Nope. What do you have to do? Complete the square. Make sure you're really careful, especially with the negative. Okay. And then I've got some other examples that describe what they look like, and you come up with the equations. Here's the assignment, and there's some matching and some ones that are a little bit more complicated and stuff like this. Good. So here's what I want you to do. First of all, pay attention to me for the next 3 or 4 minutes. I'm going to tell you one application for hyperbolas. Would you do 1 through, tell you what, see if you can get up through 15 done over the weekend. Okay? So it's not too bad. You could probably get it done before you even go home. Okay? And then I want to take a look at this right here. How many of you have seen Apollo 13? The movie Apollo 13. Oh my gosh, seriously? People will have to watch that on Monday. Apollo 13 is about the Apollo 13 mission to the moon. They had a mishap on the way there. A day or so after they launched from Earth. They had a little explosion, crippled the ship and all that sort of stuff, so they weren't able to land on the moon. And the way they got back is they actually they didn't have a ton of fuel and stuff like that. They couldn't just turn around and rocket back to the Earth. So what they did is they got to the moon, and they made sure when they got there they had a little bit of fuel so they could use their engines and get in the right place. What they did is they used, what's it called?
Themselves.
It's called a slingshot return, a slingshot trajectory. So what happened is they're approaching the moon like this. Now, where would the moon be, Noah, in this picture right here? If they're following a hyperbolic path, where would the moon be? Very good, okay? So this would be the moon. And what happens is the gravitation of the moon, it's kind of focusing that gravitation. It kind of pulls it toward it, but not enough to make it crash into the moon, just enough to curve its path. And then once it gets past, it starts to straighten out and straighten out and straighten out. Okay? So they do this quite often. In fact, a lot of the satellites that they have launched, like anybody heard of the Voyager spacecraft? I think they launched that in the 60s or the 70s. It's still going out there. It has gone billions and billions of miles. And what they do is, if the planet's right here, they send Voyager toward that so it can take pictures. But as it goes around, it starts to bend. And they actually use the gravitation of the planets to speed it up and slingshot it toward the next one. So they'll figure out how close they need to get it, what angle they need to come in at, so that they can grab that gravitation and then it can shoot it off in the right direction to hit the next planet. So say the next planet's over here. It runs kind of a straight path for a while and then it goes like that, slingshots it. So that's how they can get a satellite that launched decades ago from Earth, billions and billions and billions of miles away, and get it in the right place and stuff like that. It's pretty amazing that they can do that. Okay, That's one application for the hyperbola. Okay? Not nearly as fascinating as it should be, right? But you should, if you haven't seen Apollo 13, you'd love it. It's a great show. Okay, so do up through 15. Have a great weekend. Put 10.3 up here before you leave.